All right, class, welcome on in. So this is our recorded lecture for Module 4, so essentially week 4 of our class. So we're about a month in, and every 4 weeks is about 25%. So 25% of the semester is already gone and done like that. So just a couple of things. This will guide you through everything you need to sort of close out a couple of the tabs I had open there. One was the Wall Street Journal. I don't think we want to get into that one right now. But anyway, yeah, we want to talk about science. So I'm going to walk you through this week's module and how to get it accomplished and where you can find all of this stuff. So if we just take a look at our Canvas course right here, if I open it on up, we get the traditional, although very slow moving for some reason, welcome page that you should see. So of course, my Zoom information right up here, how to contact me, yada, yada. Everything we've seen before, except now on the bottom, we also have, let me see if I can move this. There we go. We have this little link to follow to the week 4 module. So if I click on that and we go to the week 4 module, you'll see in here the typical things that we've seen, in previous modules. So we have our discussion board first and foremost. Please remember that this is required. This is a required portion of the course. You are graded on this. So if you have not done the previous ones, please make sure you hop in and do them so you don't lose out on those points. It's worth 10%, so it's a full letter grade. This is what gets us actively participating in the class. So if you click on this week's, once again, we just have a short little video. And what we're going to be talking about this week is where does Earth fit in the universe? We're talking about Earth science in this course. One moment. So we're talking about Earth science in this course, but we need to know the context. We need to know where we are in the whole grand scheme of things. So this helps us to understand that where we are, our observable universe. And they're going to talk in this video about that term, observable universe. That almost like indicates that there's an unobservable universe. And they get to that, and it's all related to light speed and the speed of light and what that means. So you're going to hear stuff in there about the speed of light and cosmic background radiation. Those are two very important things that will help you answer this question here when they say, what is meant by the term observable universe? And I want you in your answer to include the term speed of light, because you can't really answer it without using the term speed of light. So therefore, that will be something I'm looking for in your replies, and I'll be grading based on seeing that in your replies. But this will be our discussion topic, our discussion board for week 4. And so if I hop back over, the next thing on there is just our link to week 12. I'm sorry, to week 12. I'm already 75% done with the semester in my brain. So this is the link to ck12.org. If you have not signed up for this, make sure you do that right away. That is part of a previous module I will show you in just a second. But obviously this will link you out to ck12.org that I'll go to in just a moment. But remember, the thing that we did week 2 was signing up for CK12. And so the instructions are right in here in this PowerPoint. And then once again, you have the homepage there. So it's all ready for you. So hopping back to our CK12 work. So what we're going to go over really quickly is the PowerPoint. We're going to get that done pretty soon here. And this PowerPoint will be waiting for you. I embedded it in. So this is what you're going to see tonight when you come in and when we talk about it. But this one here, this PowerPoint is strictly the PowerPoint. It is not the lecture that you are hearing right now, but it'll be there for you to scroll through in case you need to beef up the knowledge on CK12, which is a perfect segue into CK12. So a couple things that I noticed. First and foremost, people are hopping on there and people are really getting some good scores and getting a lot of good stuff done. One thing that does concern me is some people are doing the quizzes and not the adaptive practice, or they're doing the adaptive practice and not the quiz. Both the adaptive practice and the quiz are required. Even if you can pass the quiz without the adaptive practice, that's fine. That's great. That's wonderful. But you still have to do the adaptive practice because you're getting graded on it. So if you don't do that, then you are missing out on a lot of points. So we'll look at our next, our next assignment in here. So if I go to assignments, you see you have a new one right there ready to go for you. So last week we did phases of the moon. This week we're doing Earth's place in the universe. And so it's being assigned today. The due date on it is the 18th. That's just for grading purposes. I'll talk about the grade book tonight in class. But it'll be, this assignment will be there and available for you the entire semester. So just know that. So let me hop to reports real quick so I can kind of show you what I'm talking about. We can see some of the scores here. One of the things we want to make sure we do, so this is all blank. And so I have all of you sort of in this grade book. And this is sort of what we're looking at. And so some of the things that were concerning me were like, people doing the quizzes, but not the adaptive practice, or doing the adaptive practice and not the quizzes. So keep in mind, all of those are required, okay? And so with our new assignment, Earth's place in the universe, if I click on that, just to sort of show me what's in there. Last week, we only had one section, so this week we have 3. So it's going to grow a little bit as we get more involved in the class and as we sort of keep going with our studies. And so you have 3 sections here: the planets of the solar system, the inner versus the outer planets. There's huge differences in those. And then the Milky Way. And then the last thing on here is Earth's place in the universe, which is a quiz. It's less than 20 questions, I know that, so it's nothing too terrible. One thing I wish I would have shown you, and I'll show you real quick. I won't show the grade book from here on out, but since we're just starting, and it's not like any letter grades are being posted, I'm fine showing this. But so I'm recording this at 1 o'clock, and Brees has already finished the week's work. She's already good to go. So she doesn't have to show up tonight if she doesn't want to. That's awesome. Great job there. I love that. So that's always available to you. So let me show you a couple things I'm talking about here with CK12. So if I go into planets of the solar system, you're going to see here, oh my goodness, there's so many things. And this is all designed to help you answer the adaptive practice and the quiz. So you'll want to read these articles. You can do the Plix activities. You can watch the videos. You can do the activities. You can look at these study aids. And then, you have real world examples that you can also look at. So all of this is meant to beef up your knowledge on the planets of the solar system. Once you've gone through all that, then you go to the adaptive practice and you'll start to work on that. And for this, you have to get 10 correct answers. So it's not 10 in a row, but just 10 answers in total before you are complete with it. And so this is required. You got to do it. It's not that terrible. Just make sure you use everything that's given to you. So same thing with the Milky Way. You're going to see the reading articles, the videos, the activities, the real world examples, and that all leads into the adaptive practice. So you will have 3 sections of adaptive practice to do, 1 for each of the sections here, and then you will have the quiz of the Earth's place in the universe. So that is all your CK12 work. On our Canvas page, if I go back to our modules, you can see all you have here is just this discussion board and then the CK12 work, and that's all we have to do. So the discussion board is our way to interact in the class. The CK12 work is the way that I'm able to hand out classwork as if we were in class, and I can give you a worksheet. And then the quiz is how you would normally wrap up our evenings together if we were able to meet in person. But since we can't, we got to do the quizzes on CK12. So now let me go over this PowerPoint. It's not going to be terribly long. Actually, I'm going to go to this one so I can present it in big screen here. So as I go into presenting this, we are talking about our cosmic bubble. So yes, we will talk about where the Earth fits in the universe, but we're also going to focus in a little bit on just our little bubble, our solar system to be specific, and also a little bit on our galaxy, which is the Milky Way. So Earth's address. Let me see if I can move my little, there we go. I'll move my little screen guy here. So Earth's cosmic address. So you may have seen a little bit of this in the video, but we have a cosmic address the way that anybody has a regular address. So I put not my real one over here because I don't need you guys to send me a bunch of hate mail or something, I'm not saying that you would, I'm just joking. But so just the way, like if I was expecting a letter, or if someone wanted to send me something, or if I wanted to tell people where I lived, I would say, okay, I'm Jason Jorgensen. I live at this street address, 320 East Chapman Avenue. I live in this city, which is within this state, in this country, on this planet. Now, obviously, you don't have to get that detailed, but with something like the universe, we do have to be super detailed with it. And so if we want to look at Earth's cosmic address, so we are on Earth, and then as we go from there, we have our solar system. So we're getting a little bit bigger. Our solar system is part of the Milky Way galaxy, and that Milky Way galaxy is part of the local group of galaxies that we're around, and that is all within the Virgo supercluster, which is within the observable universe. So you'll learn about the observable universe in that video. That's pretty much as far out as we can see, and there's a couple different reasons why there, so you'll want to beef up on those in the discussion board video. So let's progress on from there. Why did my thing just get dark? There we go. Oops. All right, so here we go. So where are we? I'm sorry, I got my little screen here. I got to keep moving around. So we are on a spiral arm of the Milky Way galaxy. So I'm not saying this is precise, but we would be right about out in here. So we're about 30,000 light years from galactic central point. So we're just on one of these arms swinging around. And it takes us, a couple 100 million years to do like a full rotation. So the last time that we were in this position in the Milky Way galaxy, dinosaurs were stomping around the Earth. So it was quite a while ago. Why don't I keep doing this, man? Okay, here we go. I'm just hitting a weird button, and it keeps making my screen go weird. But anyway, so light time. They talked about this in the video. So it is important for us to understand what light time is, because light, like anything else, has a fixed, I shouldn't say a fixed speed. It does have a fixed speed, but when you open the blinds up, or you pull the curtains open, the light that floods into the room, it's not like it's instantaneously there. It does have to travel at a speed. So even if we shoot a light beam out into the sky, it takes time for it to travel. And so this is going to sound really weird, but if you had a planet that was 65 million light years away, what that means is that light that leaves Earth would reach this planet 65 million years later. So if they had a telescope powerful enough to look back down at Earth, they would see dinosaurs. Because they would be seen 65 million years into the past, because that light that left Earth at that point took 65 million years to reach them. So it's a weird concept. We don't need to understand it completely for this, but we have to understand what light time means. It's just the time that it takes light to travel. Now, the universe is so big, we can't say, oh, it's a bazillion, trillion, billion mile. That is just not really a concept we can wrap our brain around. So what we can wrap our brain around is how far or how long it takes light to travel a certain distance. That's light time. So light has a fixed speed. All light, regardless of the color, travels at 3.8 times 10 to the 8th meters per second. That is as fast as anything in the universe is allowed to go. Nothing can go past the speed of light. I say except the weekend there, because the weekends go fast. We enjoy those. It's just a terrible joke. But nothing can go faster than the speed of light. That's just a cosmic fact. And this gives us a useful dimension of time. Since it is a fixed speed, like a light minute would be how far light can travel in a minute. A light day, how far light can travel in one day. Light month, how far light can travel in 1 month. And then light years, which is the one that's most common to us, is how far light will travel in 1 year. I get a little excited and ahead of myself here. But so essentially, if you shot a beam of light, how far it travels in a year would be a light year. And you can sort of tell with the speed this great, 3.8 times 10 to the 8th meters per second. So you're talking 3, 8, and then 7 zeros after it. So an immense number there. It's going that many meters per second for an entire year. That's going to be a long time. But that's just what we call a light year. So some of these other galaxies that are a million light years away, we have no hope of ever reaching those. Because even if we can go the speed of light, it would take 1 million years to get there, 100 million years to get there. So light is just this interesting concept unto itself. And but it does give us a fixed speed in which we can measure a dimension of time. So our galaxy, Galaxy Kuklos or Via Lactea, that is the Milky Way galaxy, And so we are 80,000 light years in diameter, which means to go from one side of it to the other would take 80,000 light years. So that's a long time. It contains more than 100 billion stars. Our nearest galaxy, Andromeda, has the potential to have like 1 trillion stars. That's pretty nuts. So our solar system, like I said, is about 30,000 light years from galactic central point. So where we are, as you can sort of see on here, this local arm that we're on, and so this being our sun, so that's where our solar system is. To put things in perspective on how gigantic the universe is, even our galaxy, how gigantic that is, we are about 30,000 light years from the center of the galaxy there. So our galaxy is about 1,000 light years thick. That means if you sort of took this image and rotated it to where you were looking at it like a disk, it sort of bulges in the middle, and it's 1,000 light years from top to bottom, which is incredible. It gives you another idea of perspective on this. So this is what I mean when I say like it bulges. So we have like this bulge of the Milky Way galaxy. There's all this material sort of clustered at the center, and so here's our solar system. We wouldn't even register on here, planet Earth. We're so small, but this is our Milky Way galaxy. So it bulges in the middle. It's about 30,000 light years for us to get to the center. And so you can tell if we just, doubled that up, we're looking at about 60,000 light years from the thin disk part to the sun, and then a little bit more. So you're looking at close to, 100,000 light years side to side. That's a gigantic one. And so as a quick little primer, in the video, when they're talking about the observable universe, well, our universe is, 13.6, 13.4 billion years old. So when they say what's observable, there may be stuff that's further out there, but light hasn't been able to reach it yet. And so light can only travel, at that certain speed. And so if it takes us longer to see something, it doesn't mean it's not out there. It just means we haven't been able to observe it because the speed of light hasn't reached it yet, or light hasn't reached it yet, essentially. So that's like your little freebie for the discussion board that you can throw in there. So the observable universe, that's because the light has been able to travel out there at that speed. Anything that's further than that, light just hasn't had the chance to get there yet. And it's not fast enough, which is weird to say. So our solar system, to get a sense of proportion, if we had a scale model, now this is easier to do in a classroom where I can sort of work it out for you. But if the sun was a plum, so you figure, a plum size, and it is 13 feet away from the Earth, which would be the size of a grain of salt. So if you had a plum and a grain of salt, and you put them 13 feet away from each other, that's roughly the distance between the Earth and the sun. And this is what we call an astronomical unit. And that distance would be 93 million miles. But if we're looking at a scale model here, if we went from the sun 71 feet away would be an apple seed that would represent Jupiter. So we have this plum. 13 feet from the plum is a grain of salt, which is the Earth. And then 71 feet away from the plum is an apple seed, which is the size, which would represent Jupiter and all that, which kind of gives you an idea of the size of the sun. And then the whole model, if we wanted to do our solar system, the entire model would be bigger than a football field. That shows you the scale of just our solar system, not even our galaxy or our local group. Neptune, would be represented by a grain of sand that would be 400 feet away from the sun. So, I mean, this is massive scales we're talking about here. And so the asteroid belt would be between Mars and Jupiter, and you need a magnifying glass to see even the largest asteroids. That's just because they are sort of fragments, of other celestial bodies. And so you'd need a magnifying glass to see those. So that was if we just were able to scale down our solar system. And so here's a little graphic of it. This is not to scale by any means whatsoever. But so we have our sun, which is gigantic. And then we have, Mercury being the first planet from the sun, Venus, Earth, and Mars. And that gives you an idea of the scale of Jupiter. And then we have Saturn, Uranus, and Neptune. And then Pluto's up for debate. Sometimes it's a planet, sometimes it's not. But we're not going to include it here because, I don't know. I just didn't. I don't know. All right. So the terrestrial planets, we're going to talk about those first. And those are our first four innermost planets: Mercury, Venus, Earth, and Mars. We call them terrestrial because that terra prefix stands for land. for our purposes. These are also known as the rocky planets. So the consistency, varies from planet to planet, but they're all rocky. They have like a rocky surface, sort of like a crust, a rocky outer shell, if you will. So it is the four inner planets from the sun, just being Mercury, Venus, Earth, and Mars. So these are our terrestrial planets. So these are relatively small compared with the other planets in the solar system. They are dense and rocky with little to no atmosphere. Even our atmosphere, which is the thickest, isn't all that thick. If the Earth were a basketball, our atmosphere would essentially be like a piece of paper on top of it. So it's relatively thin, but Earth has the thickest of the atmospheres, and some of them have no atmosphere, which our atmosphere is one of the things that allows us to be here, allows us to live. So usually have these volatile gases are not super abundant because being so close to the sun, they sort of break apart or they burn off, if you will. So CO2, which is carbon dioxide, CH4 is methane, H is hydrogen, and He is helium. We find that the outer planets are much more, they consist of these types of gases, but as we get closer to the sun, these gases burn off. Therefore, they're not very not very abundant, these volatile gases. So we take a look at Mercury. It was named by the Romans. It travels the fastest around the sun. And in Roman mythology, Mercury was the god of travelers. How cool is that? So, and Mercury, one day takes 2 years for us. So for it to rotate, one complete rotation takes 2 years. And that is because it's tidally locked to the sun. We had mentioned tidally locked last week when we talked about the moon and the earth, why we only see the one side of the moon. But 1 year on Mercury would only take 3 months. So therefore, it is going around the sun really fast, but it is just rotating super, super slow. Sunlight temperatures there average 450 degrees, so not a very pleasant day. Venus, which very well could have been like an earlier Earth, which we'll talk about later on. But Venus was the Roman goddess of love and beauty, and it's the brightest planet in the night sky. So how sweet is that? It's the brightest out there, and it is love and beauty. How cool! So it has a very similar size to Earth and very similar composition, which makes some scientists think that maybe it was hospitable to life at some point in its past, but it almost had like this runaway greenhouse effect where carbon dioxide and other volatile gases built up in the atmosphere to make it an unlivable planet because it got so hot. So the temperature makes it inhospitable, and then the atmosphere is made of essentially sulfuric acid, hydrochloric acid, and hydrofluoric acid. So not a place where you can live. And I have on there like a portent of things to come, because if our greenhouse gas situation goes on like a runaway building, if you will, this is what our planet could look like one day. Hopefully not. All right, so we come to Earth. Earth is the largest of the terrestrial planets. We have a relatively thick atmosphere compared with the rest of the terrestrial planets. We are unique that we have active plate tectonics. We will get into plate tectonics in a couple of weeks here, but essentially that means that we have motion on the surface of our planet. These lithospheric plates constantly move around. And so we are the only planet in our solar system that harbors complex life. Is our life outside of our solar system? Probably. The numbers support it. But in our solar system, we are the only ones that harbor complex life. So we are located in what's called the habitable zone. We are like, if you remember Goldilocks and Three Bears, like the one soup was like, or porridge was way too hot, one was way too cold, and one was just right. Well, we are at a position at a distance from the sun where it's not too hot and it's not too cold. It is perfect for conditions that bring about life. So our atmosphere moderates our temperature as well, and we have a magnetic field, which we will get to in later lectures. But these are the things that sort of protect life on Earth. So Earth is not straight up and down. It is tilted at 23.5 degrees, and this tilt leads to an uneven heating of the Earth, which leads to the seasons that we get, whether it be summer, winter, autumn, Summer, winter, autumn, spring. I also love spring out there. Yeah, so we're going to get into that a lot later on, but we just want to talk about the overall general characteristics. So we're not flat. That idea is absurd and is very uneducated, uninformed thing to say. I always like to throw that in there just to make sure that we know that the Earth is a sphere. Okay, so then we got Mars. So Mars is the Roman god of war. And, it's the red planet, so you think red, angry. But so the Roman god of war, and there are two moons to Mars, Phobos and Deimos. One is fear. Deimos, I don't know if it's like evil. I can't think of it right now. So I apologize for that. But their atmosphere is 95% CO2, meaning carbon dioxide. So that's very abundant. That is not something that humans can just easily breathe in and function. So Mars, because of they do have this small atmosphere, they do get weather. Not the same as we get here, but there are like huge dust storms, or there can be storms of different varieties, like mainly like wind driven. So think like hurricane-esque or tornado-esque on the surface. And so the red color comes from what are called oxides, which gets into chemistry a little bit, but essentially rust has like that red color because it's been oxidized. And so the materials of Mars are oxidized, giving it that red visual, that red look. So there's very low surface pressure, so water boils off very quickly, which is why we usually don't see running water on Mars. There is evidence that water did once flow there, but we don't typically see it now, just because it boils off so quick. Mars does not have a magnetic field, and the core of it is most likely solidified. So we see those are two things that make it much different than Earth. We have a magnetic field, and our outer core is liquid, which generates that magnetic field. So since Mars doesn't have one, we can say that the core is most likely solidified. All right. Cool. So now we get to the Jovian planets, which are the outer planets, the last four. So Jupiter, Saturn, Uranus, and Neptune. So they're called the gaseous giants because they are massive and mostly made out of gas. So Jove, from Jovian planets, Jove was the same as Zeus, which was the same as Jupiter. So we kind of get an idea where these planets get their names. So Zeus was the god of sky and thunder. And all of these planets are many, many times more massive than Earth. Even Uranus and Neptune, they are massive compared to the size of the Earth. So Jupiter, let's start there. Jupiter was the king of the gods, and so it's our biggest planet, so it deserves that name. And so one day on Jupiter is only 10 hours. So that's an incredibly fast rotation for a planet that big. And one orbit around the sun takes 12 Earth years. So every 12 years, Jupiter makes its way around the sun once. So I'm 36, so I've only lived to see, I haven't seen it, but I've only lived through 3 Jupiter years. So I guess on Jupiter, it'd be 3. That'd be kind of weird. Almost starting school next year. But anyway, so 1,300 Earths can fit inside Jupiter. Amazing. Saturn, what a cool little planet with the ring so visible. Saturn was the Roman god of time. And so one orbit of the sun takes 29 Earth years. It gives you an idea of the distance from the sun. And one day is 10 hours long. Once again, very, very fast rotation. And so it has all those fancy rings, which are essentially icy snowballs or ice-covered rocks that are just sort of caught up in the gravity, but have not coalesced to form anything bigger. So their width is the same as from the Earth to the moon. So the distance from the Earth to the moon is the same as the distance from some of these bands of rings on Saturn. Now, much like the reason these planets, so I'm going to get to, man, I'm jumping over my words here. Pump the brakes for a second. So the gaseous giants, since they're mainly made up of gases are very light. So all of the gaseous giants are very low density. So the reason I have Saturn's density here being 0.71 grams per cubic centimeter, because the reason I have it up there is water's density is 1.0 grams per cubic centimeter. So this means that since Saturn is lighter per cubic centimeter than water, if you had this big gigantic pool and you plop Saturn down in it, it would float. Kind of cool. I don't know. I like it. So Uranus and Neptune, they are very similar, and they are more like ice giants. They're so far from the sun that those gases have almost like condensed to form ices of sorts. And so Uranus has the lowest temperature in the solar system, minus 371 Fahrenheit. That is very cold. So one orbit for Uranus takes 89 years. So, I mean, there's a chance I won't even live to see one full orbit of Uranus and Neptune there. So the axis is tilted 90 degrees. So it means instead of it being straight up and down, it's like this. And so it almost rolls on its orbit as opposed to how we spin. This would almost look like it'd be like rolling. So Neptune is the smallest of the Jovian planets out there. 1 year there is 165 Earth years. So it takes a long time for it to go all the way around the outside. And it absorbs red light, which is why it gives off that blue color. So it's absorbing all the red color, giving off the blue color, and it gives us an idea of distance, which we'll get to in later lectures. But Neptune is, the god of the sea, so it makes sense why they called this planet Neptune, with it being so bright blue, almost looking like a giant ocean out there. So that is going to do it for the lecture. That is just giving you a background on all the planets, because when you go into the CK12 units, 2 of the 3 focus on the planets of our solar system, and then we talk a little bit about the Milky Way. So this was a little bit longer lecture. I thank you for staying with me, and it's always going to be here for you to listen to, and enjoy your week and enjoy exploring Earth's place in the solar system.